All right, hey guys, here we are, problem number 7, week number 6. It says let z equal x plus iy be a non-zero complex number. Express 1 over z in the form u plus iv. All right, so let's write it out here and kind of take a look at what we can do. So if I have 1 over z, and 1 over z would be equal to 1 over x plus iy. If I want to get that into this form u plus iv, I got to multiply by the complex conjugate, which would be x minus iy. So then 1 over z would be equal to x minus iy over x squared minus I squared y squared, which will be x squared plus y squared. Okay, so then iz will be equal to x over x squared plus y squared minus iy over x squared plus y squared. All right, cool. That's part 1 complete. Part 2 says if z plus 1 over z is equal to k, show that either y equals 0 or x squared plus y squared has to equal 1. Okay, so what is z? Z ends up equaling, as we know, x plus iy. If that's equal to 1 over z, which is x over x squared plus y squared, minus iy over x squared plus y squared. If those two are equal, then that means that the real components have to be equal. Which could only be true. This could be true if and only if x squared plus y squared equals 1. So we can check that off. Or if the imaginary components also having to be true. So y would have to be equal to negative y over x squared plus y squared. That can't be true unless y equals 0. All right, so we can check that off as well. All right, let's move to part 3. It says show that if x squared plus y squared equals 1, then the magnitude or the absolute value of k is less than 2. So if x squared plus y squared is equal to 1, then x plus iy plus x minus iy, right? I have like this ghosty, right? This ghosty value that used to be there, which was x squared plus y squared, but it's equal 1. So that's now gone, is equal to k, right? So z, this is z, plus 1 over z is equal to k. All right, now, if I combine these components and x squared plus y squared is 1, then that means I have 2x, and then the iy and the negative iy reduce. So I get 2x is equal to k. All right, so if x squared plus y squared is equal to 1, then the absolute value of x, let's say x is negative, whatever, this is the equation of a circle. Therefore, whatever the x value is, it has to be less than or equal to 1. Okay? Now, if this is true, right, then 2 times the absolute value of x has to equal k. And if the max value for x is 1, then k has to be, its max value would also be 2. Therefore, k would have to be less than or equal to 2. All right, so let me say that one more time. if x squared plus y squared equals 1, the absolute value of x, its maximum value, could be 1. So if 2 times the absolute value of x equals k, which we showed right here, x's max value would be 1, therefore k's max value would be 2. Awesome. Okay, so I hope you enjoyed the drawings that I made there on that problem. Let's continue on and see what we can come up with on the next part. All right, so 7b, 14 marks. This is a sizable question, probably a paper 2 question. It looks like it's worth 22 marks, so it's significant in nature. So let's see what we can dig out here. So w equals cosine theta plus I sine theta. Show that w to the nth plus w to the negative nth equals 2 cosine n theta. I think we've seen this before, but w to the nth would be cosine n theta plus I sine n theta. All right, so that's w to the nth plus w to the negative nth. Because cosine is an even function, cosine negative n theta will actually be equivalent to cosine n theta plus I sine negative n theta will actually be equivalent to negative I sine n theta. So this will become on the outside minus I sine n theta. All right. We're going to show that this is equal to 2 cosine n theta by just adding these two things together. You'll see obviously the imaginary components will reduce and my real components will combine to be 2 cosine n theta. So check. All right, that's part 1. Part 2, let's solve this equation. 3w squared minus w plus 2 minus w to the negative first plus 3w to the negative second equals 0, giving roots in the form x plus iy. Okay, so we got to use what we know, right? And what we know is that w to the nth plus w to the negative nth is 2 cosine n theta. So I'm going to find w's that have the same power. So I see w to the second, w to the negative second. So I have 3 w to the seconds plus w to the negative second. I just factored a 3 out there. Okay, and then I see w to the first, w to the negative first. So I'm going to pull out a negative, leaving me with w plus w to the negative 1. And then leave this 2 out on the end. Okay, we're going to end up doing some factoring here in a minute, so just hang with me. So from part A, I know that w to the nth plus w to the negative nth is 2 cosine n theta. So if I have w to the second, this will be 3 times 2 cosine 2 theta minus 2 cosine 1 theta plus 2 equals 0. Now, this comes out to be 6 cosine 2 theta minus 2 cosine theta plus 2. A little added bonus here, some trig work. I can't factor this yet until this is just a theta and not 2 theta, so I've got to do a little work with that. 2 cosine squared theta minus 1 is the equivalent of cosine 2 theta. You could go other directions with it, but you'll just cause yourself a little bit more heartache. Here what I've got is I've got something I can work with now. So that means I have 12 cosine squared theta. That'll be minus 6 plus 2, so minus 2 cosine theta, and the negative 6 and the 2 make a negative 4. All right, so now I've got it in a form that I could potentially factor it. I'm going to factor out a 2, just to maybe make my life a little bit easier. That'll be minus cosine theta and minus 2. I'm hoping I can factor this. And in fact, I believe we can. That comes out to give me 3 cosine theta minus 2 and 2 cosine theta plus 1. So that means cosine theta awesome, equals either 2/3 or cosine theta equals -1/2. Okay, I'm going to do some work here and some work here. So if cosine theta equals 2/3, that either puts me in the first quadrant or the fourth quadrant, right? So that puts me here, cosine 2/3, which would make this side root 5, I believe, using Pythagorean theorem. Or it puts me down here in the fourth quadrant, symmetrically very similar, with a -root5. Okay, so what that tells me is if I'm solving for W is a complex number, and W has a real component, which has a cosine, and an imaginary component, which has a sine. So if cosine of theta is 2/3, then sine of theta is either equal to plus √5/3 or minus √5/3. All right, so now let's sketch out cosine equal to -1/2. That would put me either in quadrant 3, so -1/2. That makes this a √3. Okay, that's in quadrant 3, and then same thing in quadrant 4. -1/2 makes this a -√3. Therefore, that makes the sine of theta in this case either √3/2, which you could, obviously see using the unit circle and maybe not having to sketch this out, but either that or -√3/2. So I get 4 values. Okay, W either equals 2/3 plus or minus I√5/3. I'm getting the 2/3 here from this example, or W equals, I can go this way with it, -1/2 plus or minus I√3/2. It's number 7, guys. That's 22 marks. That's a good one. Anything you can do to see complex numbers in a very challenging form is good for you. It helps you to kind of understand the depth and just the complexity, no pun intended, of working with these complex numbers. So hope it went well. Shoot me an email or we can meet up on Google Hangout or whatever and chat through it if you need help. All right, have a good night. See you later.